Okay, good afternoon, everybody. Assalamualaikum warahmatullahi wabarakatuh. Welcome, everyone. Welcome, students, and also colleagues to this session. This is actually course TK 4046 about fundamentals of process metallurgy. And I'm very delighted to have Dr. Abdul here, Abdul Khaliq, PhD. He was my PhD colleagues, yeah, when I did a PhD in Swinburne. Okay, before we start, I would like to explain about the biography of Dr. Abdul. So, Dr. Abdul is now assistant professor at the University of Hale, Saudi Arabia. He has a lot of experiences. He received his PhD in metallurgical and materials engineering in Swinburne University in 2013 in Melbourne, and he has been working in MIT, MIT University Melbourne, KU Leuven University Belgium, and now in University of Hale, Saudi Arabia as assistant professor. He also has award by Marcus Grossman Young Author Award by American Society of Metal, ASM, in the USA. And he's also been working with Umicore. Umicore is a company working on recycling, metal recycling in Belgium, and also in Malaysia, and also in Autotech in Australia. So he has a lot of things to explain, and now he's going to explain about the e-waste recycling way forward. So for the students and also for Dr. Abdul to know that we also now have a chemical engineering seminar parallel with this one, and that the theme is circular economy. So this is very related to your explanation today. So I think this is going to be very good for the students to know a lot about circular economy, and for this case in the field of e-waste recycling. Okay, the students have learned about pyrometallurgy and hydrometallurgy, and regarding to the resources in Indonesia, like for example, iron ores, steel, and also copper. All right, Dr. Abdul, the time is yours, so you can start.
Okay, thank you so much, Dr. Vinny, for your nice introduction. I also want to thank you for your invitation. And of course, I would love to join again, if the opportunity comes along. So actually, today we are going to talk about electronic waste recycling. Basically, before we start, I just want to give the brief background of this work. This work was done as a part of my post-PhD assignment, and here I want to take opportunity to thank my previous colleagues, my bosses, Professor Jeff Brooks from Swinburne University, Australia, Dr. Muhammad Akbar Ramadani. So nice to him, actually. He's so kind. He was my PhD supervisor, and also, we work along in this project on the e-waste recycling. So the data, most of the information or the data I'm going to discuss and share today is taken from that work. So I have also give the reference if somebody is interested to learn more about e-waste recycling. I would recommend to check our papers. So probably they will give more insight because of the limitation, of course, for the time today. So I won't be able to cover all of them, but I will try to give the brief introduction and the science behind electronic waste recycling. What are the possible routes? What are the industries that are leading in this area? And what is the way forward? Okay. All right. So first of all, if I just want to, sorry, I'll just bring it here. Okay. Yeah. So first of all, how do we define electronic waste? Electronic waste, there's two broad definitions at the moment. One is the European waste electrical and electronic equipment. It's WEEE is like the waste, electrical and electronic equipment. Based on that, basically it contains all the components and sub-assemblies, or even the consumable that are discarded from the electronic components at the end. But the Basel Convention, like there was dealing with the electronic waste action plan all over the globe. So based on that, it has a broad term. It takes many other, the components. For example, it takes household devices, for example, refrigerators, air conditioners, cell phones, of course, personal stereos and consumable, consumer electronics to computers. All of these that we use in terms of electrical and electronic component that comes under the electronic waste definition now. So it is a bit of change. European, they takes about the consumable related to the electronic components, but in the Basel Action Network that had some broader spectrum. So, in this slide, this is the work done by 40 et al. Global e-waste monitor in 2020. What's happening at the moment? What is the condition of electronic waste? At the moment, what I use a term to my students, I'm leading some projects on this area, in this area as well. I say it's like, emerging pandemic for the world. As we are passing through the pandemic of COVID-19, this is going to be also a kind of pandemic. Why is pandemic? Because at the moment, the growth is exponential. The electronic waste is increasing at, a high rate. So what are the possible drivers for this higher electronic waste? Input is, for example, we have the higher levels of disposable income. People now have a bit more money, so they can afford gadgets, they can afford new mobile phones, they can afford new electronic equipment, and also the urbanization and industrialization, all of these three things. But at the same time, people are per person are using higher electronic components at the moment as they used to do 20, 30 years back. Also, these electronic components don't have much life now, short life. We take a mobile phones after 2 or 3 years, we start feelings that it's not working well, software is not working, so we need to change it. And also the few repairs options, so not much. All of these parameters or all of these inputs lead to increase the electronic waste globally. If we talk at the moment, currently in 2020, 2019, at the moment, about 54 million tons of electronic waste has been generated in the world. And of course, the major share coming from Asia because of the population, but per person growth, if we just have a look here, we can see that, of course, the developed countries like USA, Canada, Western countries, Europe, the per person is about 20 kilogram per inhabitant. That's a lot, there's a lot. But their growth is comparatively, is okay, 1 to 2%. But if you come back to Africa and Asia Pacific, the per person e-waste generation is okay, but their growth is comparatively double of them. So, all of these factors are, indicating that the electronic waste is growing exponentially. So there is a need for the, the governments, local governments, and a global action plan so that this can be tackled, efficiently. If we take the example of that one, about 4,500 Eiffel Towers, equivalent to that, even more than that at the moment, because this report is 2016, but according to latest, about 5,000 Eiffel Towers, equivalent to that, the e-waste has been generated. So why we are worried about the electronic waste? That's the common question. Of course, we have like the community exposure. The community is exposing to this one in terms of food, water, air, all of these parameters, because when electronic waste is, normally electronic waste was used to dump in the landfill. When electronic waste was dumped in the landfill, it leaches out with the passage of time, and we have the heavy metals, cadmium, lead, zinc. All these heavy metals, when they comes into the groundwaters, ultimately that water is used for vegetation, that water is used for drinking, and rivers, and so all of these things related to the environmental contaminations ends up in the human life. And also the occupational exposure. For example, we have the electronic waste recycling facility. It's not properly maintained. A lot of fumes are generated over there. And then, of course, that's not good for the health of the occupants. Similarly, children playing in the playgrounds and in the rest of the areas. These are four major areas that are, a major concern at the moment, and of course, for the future. So what how the electronic waste look like? Of course, we have mobile phones in our hands. I used to say, if somebody gave me 10, 20 mobile phones, so probably I can process them in my laboratory and I can return maybe, few milligram of gold and silver to them. That's interesting, interesting thing and practical thing, of course. But at the same time, I also encourage a lot of my colleagues, and my students as well, because they're more energetic. I believe I'm also at the moment. So these, students can think about as a business case, especially this electronic waste. At the moment, you can find it all around you, all around in every country. If there is a proper, guidance and people have some passion in there, so this is a good business as well. Processing them in terms of environment to benefit the environment as well, but at the same time make some good money out of this business. So you see these mobile phones, when they are wasted, if we just dismantle mobile phones, you will end up with all of these some sub parts. So the major parts from these mobile phones, you will find, of course, many kind of materials are used, ranging from ferrous, non-ferrous, that I will discuss later on. But the most important component in terms of precious metals is this printed circuit board. That's called PCB. So you can see these these circuits where the electronic components are connected with each other with higher conductivity point of view. So they use gold and silver in these alloys. For example, lead alloys, they use silver in there, and also the gold as well. In terms of the material distribution in electronic waste, if we carefully see what's in there, first of all, this diagram gives the indication we have about 38% ferrous component. This distribution is based on, of course, on some data in the literature. You can get this reference in our work. That paper was published in 2014, and I take pride on this paper because that has been cited more than 300 times, and it has been downloaded more than, I think, 50,000 times. So that's a big number, and that shows the significance of the work. So what's in there? We have ferrous material, we have non-ferrous, we have plastics, glass, wood, and some other components. Of course, in the ferrous and non-ferrous, the precious metals and the more significant component that comes from electronic waste is in the non-ferrous component. If we talk specifically about the PCBs, printed circuit boards, three major materials we can find in them. For example, we have the metals, we have plastics, and ceramics. Of course, the metals component is about 40%. And this metal components contains copper. Of course, copper's non-ferrous, like copper, we have lead, and then gold, silver, some other precious metals. This is a part of the printed circuit boards. Along the way, if we try to further dig into to the materials that we get from the electronic waste, we see the most valuable metals. What are the most valuable metals are, for example, we have gold, silver, but their composition is given in ppm, that is parts per million. Okay, so this like the about 2000 ppm to 1000, it's little bit exaggerated, I believe, but this range that's like a higher number anyway. If we check the valuable metals, so gold and silver is the higher in ppm. And then of course you can see also, like we have a platinum, we have indium, we have tantalum, we have selenium, and we have germanium, gallium, cobalt. All of these metals are valuable metals that if we process electronic waste smartly, considering all the considerations how we can get the maximum output, so we can make a good good money out of that, and we can also benefit the environment. In terms of precious metals, if we just try to see which component we need to target to get higher electronic waste, which component we have to target for higher precious metals content. So you can see the mobile phones has like compared to the other had 93%. It's not about 93% of mobile phones, but 93% of overall the gold precious metals. PCB comes at number 2, and then of course we have the calculators as well, TV boards, computer boards, and also the DVD players. All of these has a certain level of the precious metals in there that we can tap and get benefit from there. Okay, towards the now we came to know that the electronic waste itself, the global trend is exponential increase, is increasing at a very fast rate that we don't want, basically. If we can't stop that one, so then we have to think electronic waste management. How can we manage that one? And there's the 3 possible, first of all is the waste prevention. Probably, that's the one thing that can be done. The second one is the recycling. We do the proper recycling of the electronic waste, and then we reuse them and then close the loop. Then we close the loop of that one. That's the one way of the material is coming from, of course, from the mines, is being used in the electronic waste. For example, we have a copper, we have gold and silver, and then we extract that one through the recycling route, and then resend into the loop, resend them back to some application, to the electronic waste or some other application. This is how we can close the loop for these elements. And that comes under the overall umbrella of circular economy as well. Okay, and further to the management of the electronic waste, we know that the electronic waste, once it's generated, there are 4 possible ways at any local council level or a country level. Number 1 is, of course, the e-waste formally collected. There is a collection system for electronic waste, because this is not something like traditional conventional mining. We are not going to mine and get the ore and process and get metals out. It's not like that, but it's called urban mining. Urban mining is much different from the conventional mining, because in urban mining, like the electronic waste, what we need to do, we need to collect this bit and pieces from different parts. So there is a strong network. It has to be a strong collection system so that it can be collected at the processing facility where we can efficiently process it. So number 1 scenario can be the e-waste that can be formally collected. Number 1 is, like what the councils do nowadays. I think they also introduce like the electronic waste bins. So people have the electronic waste, if they have the excess in there or it's a waste, so they can dump that electronic waste into the recycling bins, and that can be later on treated by the any industry or a facility where it can be processed efficiently. Then number 3 scenario could be the electronic waste that is collected outside of the formal systems in countries with the developed e-waste management infrastructure. And if there's a e-waste the processing infrastructure is there, so they can collect this electronic waste, and of course they can process it. And the number 4 scenario is there is no infrastructure. There's no like the formal collection, but there is the infrastructure for e-waste. So basically, these are the different scenarios where we can manage electronic waste at a local council or a local government level, or a country level, or even globally. So once electronic waste is collected, so next step is we need to start recycling. So basically the recycling step, I mean, we are not talking at the moment about the data collection that can be done by another department of, in the recycling facility. They can take off the data, just, do the reflective settings, delete the data confidentially. And after that, we have the electronic, electronic component with us. So the first thing is, that should be done is we have a sorting facility. Okay, in the sorting, the sorting and dismantling. In sorting and dismantling, what is done? We try to collect and try to separate those parts that can be reused. I think there's a smart approach, of course, and there's a logical approach. There's no need to recycle those components that can be used and their life can be extended. For example, the computers are refurbed for the further use. Their life is extended. After sorting and dismantling, so the first approach or the first step is the mechanical processing. Okay, in the mechanical processing is done the size reduction and the manual sorting. So during this process, the separation of the wirings, metals, and plastic is done. That goes to the, if we have the wirings, and in the wiring we have a copper and we have a plastic, copper is separated from there. That can be, that can be processed in the copper smelters or a secondary copper recycling facility. And the other plastic is used in the plastic industry or a facility. After the mechanical processing, the next step, of course, is the vibrating, screen. In the mechanical processing, we reduce the size, we break that, we do the crushing of that, as the crushing setup. We do the crushing of that, and after that, we have the vibrating screen. In the vibrating screen, the first thing we can use is the magnetic separation. By magnetic separation, you can separate ferrous metals. These ferrous metals, during this process can be separated, and they are sent to the steel industry for further recycling. And then after magnetic separation, the eddy current separation, that is used for the non-ferrous metals separation. These non-ferrous metals will contain copper, it will contain aluminium, and gold and silver and lead and the other components, other metals. Then we have the density separation. In the density separation, like you can further separate the plastics from there, and then we have some disposal. So at the moment, the disposal will be disposal amount will be very less. That can be landfill, but at the same time, there are some work being done by research groups. For example, I know in the KU Leuven, what they do, they're using some oxides, slags to make the construction materials. So I mean, in that case, even the complete loop of this product can be closed with a zero waste. Okay, so there are two approaches. Number one is the hydrometallurgical route for electronic waste recycling, and then the second one will be the pyrometallurgical route. But in today's presentation, I will focus more towards the pyrometallurgical route. But again, there is some information related to the hydrometallurgical route as well. But if you want to learn more about that, of course, you have our papers. You can get some information from this paper as well. Okay, so first of all, when we have the electric scrap, this scrap will contain copper, aluminium, of course, iron, tin, lead, zinc, nickel, gold, silver, sorry, this G is double, platinum, and non-metallic components. We need to size this electronic waste to shred them. After shredding, so we do the again the magnetic separation, eddy current separation steps, because if we take the electronic waste, you cannot do the acid treatment of all of that material, because that's not useful, because a lot of material can be separated at the early stage. So what you can do, iron and steel fraction and aluminum fraction, that can be separated here. But after that, with the residue of the magnetic and eddy current separation, we have the copper, tin, lead, zinc, we have a nickel, silver, gold, and palladium, and some non-metallic elements. Then we do the solder leach treatment. Solder leach treatment is used to recover solder by electrowinning process. The solution goes to the electrowinning refinery, where we can extract this one. And after that, the residue of the solder leach, the non-metallic components, that's about 65% of the PCB, that will be separated at this stage as well. So the residue of the solder leach, of course, this and then it contains copper and the other precious metals. Then you can do a further copper leach treatment, and the solution that can be done for is sent to for the copper recovery through the solvent extraction method. And then we have the residue of the copper leach will have zinc, nickel, silver, Au, and palladium, from where you can extract the precious metals. And then at the end, of course, you will also have a nickel and zinc. So these hydrometallurgical route have many limitations. Of course, one of the limitation is, that the dissolution kinetics. Whenever you have a solid being dissolved in a liquid, the dissolution kinetics, either it's a room temperature or it's a very high temperature in the pyrometallurgical processes. It all depends. I mean, of course, along with the other factors, is the surface area. How much is the surface area? So to increase the surface area, you need to reduce the size of the electronic waste, so that you can have efficient dissolution. With the minimum time, the dissolution kinetics can be increased, of course, by the increasing the surface area of the particles being dissolved. But in this process, about 20% of the precious metals is lost because of the mechanical, the processes, early mechanical processes. So if you lost 20% of the electronic waste in the mechanical processing, of course, this is big loss if you look at the bigger picture. Then the solvents or the acids that are used during the hydrometallurgical routes are not environmental friendly. They are not not recommended. Even the cyanide, this is a very dangerous leachant. That's only used in the gold mines with the special protocols. And of course, at the moment, they pose a serious health threats to the occupants, inhabitants. Then the next is kind of approach in the hydrometallurgy is the halide leaching. Halide leaching is very corrosive, and also the corrosive and the oxidizing conditions. Due to these limitations, you have to have a special kind of equipment, for example, stainless steel and rubbers equipment. That's also not that like the environmental friendly and easy. Also, the cost with the theory leachants, the high cost consumption, that is only used for the concentrated gold ores, not for the low grade, because the electronic waste comes under the low grade, because the composition or the amount of gold and silver is not that high compared to the concentrated, the gold ore. Of course, and then we have the thiosulfate. There's also the process is much slower, and also the final component again is come on the at the PM, like the precious metal lost during the dissolution. So if we try to summarize the hydrometallurgical routes could be good for a very small scale processing. but you need to be careful what kind of leachant you are using. And also there is a significant loss of the precious metal along the route. So that's why if you are going to treat a global, pandemic type things, I mean, it's not viable to go on a very small scale. Of course, at a laboratory scale or at a very individual scale, you can say a very small scale, you can do the hydrometallurgical route, but overall the efficiency is not good. Then so what? So the next step or the next possible route is a pyrometallurgical route. In pyrometallurgical route, there are obvious two ways. Number one is the copper smelting route, is a secondary copper smelting route, and a secondary lead smelting route. Why we use copper and lead? The reason for that is because copper is a base metal. Copper is a base metal for gold and silver, and technology, for the copper processing, secondary copper processing is very well developed. We don't need to reinvent the wheel. Rather, we have to adjust the secondary copper smelting to process electronic waste and to get the value in terms of gold and silver out of this process. Similarly is the lead smelting. Lead smelting has also been used for many years. Technology is developed, and this is what we can do. We can also use the lead smelting route to extract gold and silver. During the copper smelting route, what we need to do, of course, we have a PCB. In copper smelting, we are not going to add ferrous material in there, like the plastic in there. No, we will only separate the printed circuit boards. Okay, printed circuit boards that contains copper, that contains nickel, gold, silver. They also contain some silica, some alumina, but at the same time, the feed for the copper smelting route will be the metallic scrap, copper scrap. So metallic copper scrap that contains copper and the oxides of copper, tin, zinc, and nickel. That comes like as a metallic copper scrap. This is a composition. Of course, the majority of that is the copper metal itself, not oxides. The exact composition you can find in our paper. Then you need to have a firelight slag. Okay? Firelight based slag is used that contains the iron oxide, calcium oxide, and silicon oxide. This is also called FCS slag. The ratio of iron oxide to silicon oxide is 1:2. And then we have the metallurgical coke, about 90% carbon. Of course, there are some other impurities in there. So 4 components. In secondary copper smelting route, you have 3 components. Number 1 is the metallic copper scrap. You have firelight slag, and then you have metallurgical coke. 3 things. But if you are going to use as a case study for the copper smelting, the electronic waste through the copper smelting, you will use the printed circuit board as a 4th component. I mean, how we do the reduction process as a metallurgist, as a pyrometallurgical engineers, or metallurgical engineers, this diagram is very well known to us. This is called the delta G lingam, a lingam that gives the stability of oxides with temperature. Okay? So in this case, we can have a look. We can see that this minus 10, minus 20, this is like the delta G value for the oxides. We know that most negative delta G value mean that compound or the substance is more thermodynamically stable at that particular condition. For example, we have 700 degrees centigrade. At 700 degrees centigrade, we can see zinc oxide is the most stable compared to carbon monoxide. But when we increase temperature at about 955 degrees centigrade, roughly, thermodynamically, we can say that carbon monoxide is the most stable, oxide compared to zinc oxide, tin, lead, copper, nickel. All of these oxides are present in the copper scrap, okay, in the copper smelting route. So basically, from this diagram, we can predict that if we treat our copper that contains these oxides at temperature about above 1000 degrees centigrade, yes, we can reduce these oxides with the help of carbon monoxide to convert them back into metallic state. So in the copper smelting route, I mean, there's the stages are like the major stage is reduction. First stage is reduction. Second stage is oxidation, and then we have the the refining stages. So in reduction stage, whenever you have all your input material, that input material is your carbon coke, okay, and you have some list of oxides that are present in your feed material. So what will happen? This carbon will react with oxygen to make carbon monoxide. Okay, when the carbon monoxide is there and you have the heat and the temperature, you have to set the temperature based on this, adjust the temperature based on this, diagram. So when you have that particular temperature, under those conditions, the possible reactions that can happen is the copper oxide that is present in there will be reduced with carbon monoxide, and you will get copper. The bar below shows this copper is in solution form. Solution form means the example of that, our boss used to give, like, Jeff Brook. He used to give, like, we have a coffee and we put sugar in there. So the sugar, when sugar is mixed with the coffee, it makes sweets. Now we cannot find any solid sugar at the bottom. So all sugar is a part of the coffee. So this sugar is now in solution form, okay? So that's why this copper will go into main phase, the liquid phase. That of course is a copper in this case again. And then similarly, we have a lead oxide. Lead oxide will also be reduced with the carbon monoxide. You will get the lead. Similarly is the reaction with all the other elements. And there is also a possible reaction that you have a copper oxide, and then copper oxide will also be reduced with iron, with iron to make the copper. So my point is, during the reduction stage, all oxides are reduced with carbon monoxide and they come into the solution phase, okay? But the gold and silver, they were present in printed circuit boards. They will become a part of now copper in as a solution. So now we have collected copper and a list of metals and gold and silver into our solution. Now we will treat our solution to extract these metals. So there is a relationship that talks about oxygen partial pressure conditions, because the oxygen partial pressure conditions that represent the reduction conditions of a process. We have we modeled and we predicted with the help of XAGE, at different oxygen partial pressures, what will be there, what will be the copper purity with temperature, what will happen to the copper purity with temperature. Look, overall, when we have a highly reducing conditions, under those conditions, the copper purity will increase, of course. But at the same time, we will also lose copper in fumes, So we will lose copper in fumes. That's why, there is the conditions like we use 10 raised to power -7 partial pressure rather than 10 raised to power -10 or 11 or 12. And also to achieve those higher conditions is really challenging. And Winnie knows about that, because when she was doing her magnesium, separation experiments, I know it's not easy, isn't it? Yeah. So that's not easy to achieve that anyway. So anyway, so basically overall these cases, now we will discuss about, we have 50% feed electronic waste, and another case is 0% electronic waste. A simple, the secondary copper smelting route. Okay, so there was here was the purity, sorry, in this diagram was the purity of the copper. And look, during the reduction process, the copper we achieve, that is about 80%, 85% pure. Even it can go up to higher, percentage, but you need to have a higher oxygen partial pressure that we don't recommend basically, as I said, because of the loss of copper. So the black copper is not a pure copper. Okay, black copper composition, the concentration of copper in black copper is about 85 to 90%. But you have other elements, like you have now zinc, you have a lead, you have a nickel, you have a gold and silver, all in solution in the black copper. So here, during the reduction processes, the challenge that is faced during the electronic waste again is also you have some kind of spinels that form. I mean, one, of course, zinc oxide is the solid phase there. If to minimize that zinc oxide or other solid phases, you need to increase temperature. That is again is also challenging. It's not that straightforward and simple. You can see if you have 50% electronic waste, so the minimum processing temperature is 1300 degrees centigrade, because at 1300 degrees centigrade you can bring all solids into liquid state, okay, and then it will be easy. Otherwise, when you are doing some pyrometallurgical process and you have a lot of solid phase in the form of slag or some solid phases, so this will reduce the overall reaction kinetics, and that is the process become stubborn, and that is not easily to handle and monitor. Okay, so basically the challenge when you will use the electronic waste, of course, is the formation of the solid phases. So this is another one of the challenge that you need to tackle when you're going to work in this field. So slag composition, you can see if we modeled between 1100 to 1600 degrees centigrade. For example, at 1100 degrees centigrade, if I just talk about the one zinc oxide, zinc oxide is coming about 30%. But if you increase the temperature to 1600 degrees centigrade, the zinc will be vaporized. It's become volatile, because zinc is not stable at higher temperatures. So zinc oxide will go off as gases. Similarly, there will be, for example, this is related to the silicon oxide. Okay, so the silicon oxide component is less at low temperature, but at a higher temperature, this component will keep on increasing. Okay, this is also related with the oxidation, the steps as well. Similarly, some other, the slag phases that we have, iron oxide, silicon oxide, calcium oxide, and some alumina, their composition will change as we change and increase the temperature. Okay, one of the biggest challenge when electronic waste is treated pyrometallurgically, that is related with the emission of gases. What kind of gases that are generated. These gases have, like the nitrogen oxide, we have sulfur oxide, sometimes you also have zinc as a dust, you may have lead as a dust, but the chances are very less. That happens at a very high temperature. And you have the hydrogen oxide. So all these gases are not environmentally friendly, and it's not like good in terms of health. So this is another parameter that has to be optimized for the efficient the processing of electronic waste. I think I will just stop in here. I'm going to give you 2 minutes for the audience if they have questions so far, so they can ask.
Yeah, so now it's 38, yeah, in my time, Abdul. So, Dr. Abdul, okay. So, I would like to invite questions from the students. This should be very interesting, and the students also know about Ellingham diagram, know about the basics of reduction of metal. They just had exams. So, okay, do you have any questions? Who asked questions?
There's two reasons. One reason could be if the presentation is too good for them and they know everything. Yep. Another reason is maybe I did not explain them well. These are the 2 reasons, for no question.
Is
Hello,
yeah, yeah,
I'm
hello. Okay.
I'm Zahir from ISIT.
Right.
How are you, Zahir?
Dr. Saab, I want to ask a very simple question. Have you separated rare earth elements from the scrap?
Actually, not in this study, I'm sorry. We simply focused on gold and silver cases initially. We haven't done practically on this one, rare earth metals.
Any experience or any related study you have gone through?
Actually, our main work was electronic waste recycling. And electronic waste recycling, the obvious elements are gold and silver. Okay. And our major work was on this field. I'm sorry. That was not related to the rare earth metals.
So another simple question is that is there any rare earth elements in electronic scrap e-waste?
I think if you look at the composition, the diagram I shared, and you can also refer to my paper. I mean, there's some scandium, indium, cobalt. Some of these metals are a part of that one. But the composition, of course, is very, very low. To treat them hydrometallurgically or pyrometallurgically at the moment is really challenging.
Yes, I know the hydrometallurgical route we are separating here in ISIT.
Mm-hmm.
This is very complex and very complicated. I know
Yeah,
the
yeah, yeah.
complexities.
I mean, look, basically, I agree with you because this study deals thermodynamically and the processing routes itself. Okay. And of course, if you go in more depth, you will come to know what's happening there.
Okay, okay. Thank you.
Thank you.
Okay,
Thanks so
thank
much.
you.
Okay, I think we will just move on and we will try to give at the end some more time for questions because I think I have a lot of.
Yeah.
Okay, so basically in the copper smelting, if we talk about the flow sheet itself, so we have the copper secondary source. Uh, in the secondary copper source, as I mentioned previously, we can add the copper, scrap, and then we can add coke, slag, and also electronic waste. Okay, PCBs basically. Now, electronic waste mean PCB, printed circuit boards. After them doing the pre-processing of that one, you can put to the high temperature reduction process. High temperature reduction process will give us a black copper. I mentioned, I showed the previous diagram. Black copper contains like 85 to 90%, depending upon the process itself, percent copper, and that will have all the other elements in there. And then from there, you will get metal oxides, dust, and some the valuable metals will come in the black copper, and then you do the oxidation of the black copper. When you do the oxidation of black copper, that I will explain in the next step, you will increase the purity of copper. You will increase the purity of copper, and you will reduce, you will oxidize the volatile elements out of the copper in the form of their oxides. Then we have the fire refining steps, electrolytic refining of copper. When the electrolytic refining of copper comes, because these steps are already developed. This is nothing new in this, the route. This route is already there. Secondary copper smelting. The only thing is we are adding in the input material a printed circuit board. Because we put the printed circuit board, because of that, their solution thermodynamics will change, and their slag and their fumes that will change. Okay, so once we have the electrolytic refining of copper, pure copper will come at 99%. You can separate that one, and slime, the gang of this electrolytic refining will be slime, is called slime, that has like the precious metals in there. And from there, you can do the electro binning step of this slime, and then separate the precious metals from there, and waste will go into the waste. Again, this is the diagram that I developed during my, post PhD work. And then later on, that was published by our colleague, Godred et al. In this one, again, this is done with the help of HEC chemistry software. Vinny, you know very well about that HEC chemistry. So we have this process flow sheet. So we give coal, slag, oxygen in there, and we have e-waste copper scrap, and then goes to the reduction furnace. We set the conditions for that, oxygen, partial pressure, temperature, and all these things. And we have like the outcome of this one. We have the metal and metal oxide dust. That is the first, off. And then we have the exhaust gases. And from there we have a black copper. Okay, black copper will go into the oxidation furnace now. Now we will try to make understanding of that one. First is the reduction process. The second one is the oxidation process. In the oxidation process, you have a carbon flux that we add in there. We add carbon, flux, and oxygen. And during this process, what's happened? We have the slag oxidation, a slag that is produced during the oxidation process. We have some solid monoxide, and then the composition of the purity of the copper is increased to more than 99%. Okay, and that kind of copper is called the anode copper. That the anode copper. Then we do the fire refining, electro refining, and from electro refining you get the cathode copper, and then slimes, as I mentioned earlier. This is the flow sheet for that process. So we have the gold and silver gang, this tin oxide from there, because tin remains there at the end, because you cannot do the oxidation of that one. You cannot do volatile that one, because the volatile elements, for example zinc, that can be easily removed, because zinc become oxides and become volatile, and even the zinc itself become easily can be removed. So this is the flow sheet diagram. And moreover, if we just look at the mass balance, I will not go into too much detail of that one, but this gives understanding. If we have a one processing unit, so how we do the mass balance of that one. So the mass balance itself, we have the e-waste 5.94. These figures are in terms of tons. Okay, in terms of tons, when we did the calculation using the HEC chemistry, so we give these inputs. And then we have the copper, about 6 tons. We have the FCS slag, like the iron oxide, calcium oxide, silicon oxide slag, okay? 0.42, and then we have a coke 0.08. We have oxygen, enriched air 3.42. Put into the reduction furnace, and then we get black copper, like 6.48. But the B, actually A is a case with 50% electronic waste. B case is without electronic waste. Okay, but the feed is overall feed is same for them. Input is same. So you can have a look on the black copper. In B, you have a more black copper, 9.61, because you put the input material as a high amount of copper in there. So that was the reduction stage. After reduction stage, the next stage is the oxidation stage. What we do in the oxidation stage, we have this iron, zinc, tin, and lead. All of these are now impurities in black copper. Now we need to remove these impurities from black copper to increase the purity of copper. Okay, so what we do the oxidation of this one. So we inject some hydrocarbons, we inject oxygen, and we do the oxidation steps. Iron become iron oxide, go into slag. Okay, as zinc react with gas, oxygen, become zinc oxide, that will also go into slag. Tin goes to slag, and similarly lead will also go into slag. But what will happen, the gold and silver that we started with, they will still remain in the copper. So this is the oxidation state. We put the black copper now in the oxidation furnace. Okay, and we give input carbon, we have oxygen, we have flux, right? We get some kind of oxides, metal and metal dust, and then the output of the black copper will be the anode grade copper, that is about 99 point, more than 99% pure copper. And this is the oxidation step. So we did the oxidation step at one by one, and then add the purity into the previous one. That was a very tricky job. I remember a lot of iterations on the thermodynamic we have to do, and you can see we started with 88%. We started with 88% black copper. We start the oxidation steps. These steps are in terms of minutes, like, I mean, it's a one cycle of oxidation. And we did one by one until we reach more than 99% purity in copper. And similarly for the 0% e-waste, this is the same trend. But at the same time, you see during the oxidation state, what is happening? Our gold and silver, the concentration of them is increasing. They are not coming from any source anyway, that was present in black copper, but now we are removing other impurities elements, and the concentration of gold and silver is increasing. There's nothing happening to them basically. Is there. This shows that they are not lost during the oxidation step. They are not being lost in terms of gas or some reaction, because they don't make any oxide or they become fumes anyway. So, and another element that is impurity is zinc in the black copper. So you can see like after few minutes of the oxidation step, all of the zinc is reduced in the form of zinc oxide gas, in the zinc vapors or in the zinc oxide. You can easily remove that one. Similar, during the oxidation step, you can also predict the removal of tin, lead, and nickel, these impurities. So the concentration of these impurities, you can also see how this is decreasing. You can see the nickel is like a benign type element that do not make like the nickel oxides when it's present in tin and silver and copper. So that's why that removed. And first of all, the element will go is the lead. The second one is tin, and then the nickel. Nickel and tin is a challenge again in the copper smelting route, because they remains at the end process as well. So now the next, of course, the couple of steps is the fire refining. Fire refining, we have an anode grade copper that goes into the fire refining process. So what we do in fire refining, again, we inject some hydrocarbons, we inject air, and we made some off gases. And why we do this one? We do this one to remove the last bit and pieces of the lead and zinc and tin that's still there into the anode grade copper, to improve or to increase the purity of the copper. The output of this process, of course, we have like the electro refinery, the electrical grade copper, like the very pure copper that go into the fire. Sorry, this is again fire refinery. This one, electro refining. Yeah. So the high purity copper comes into the electro refining. At this stage, the copper contains gold, silver, and any precious metals, and a very small amount of tin and very small amount of nickel in there. And then here you can do the electrolytic refining and extract the copper, like the normal process where how the copper is made, the electrolytic refining, and the gang of that you can treat to extract the precious metals. See, you have a precious metal refinery. The slime that is coming from the electrolytic refining comes into this refinery, and then from where you can get the gold and silver out of that, and gang is a tin oxide or some other that go into the waste. So one of the major concern in the oxidation state is the loss of copper. Okay. So the loss of copper is also a concern that we need to consider how much copper we are losing. So based on that, we have to optimize our process. We can see when we are using the electronic waste. So we need to tailor the conditions in such a way that we have a danger of losing copper in the form of the copper oxide. So this is a challenge where we need to work out to improve the process, overall process itself, so that we have a minimum loss. So pyrometallurgical routes again have some limitations. Very short time. You cannot remove plastic; it burns. You cannot remove iron and aluminum because it goes into the oxides. Okay, and you make some hazardous emissions, and also the investment is a lot, not less investment. The fine dust and the some gases that forms again emissions is not healthy, so you need to have a very good control of that one. when you have a ceramics component in the slag, that increase the viscosity of slag, and that is not good. Of course, it's cause a problem for the process itself. Recovery of the the precious metals is very good, but if you join the first part, electronic waste recycling should be pyrometallurgical route overall, and the second part, of course, will be the hydrometallurgical route. So if you join them smartly, you can have a very good recovery at the end. Now, quickly, I will introduce the companies that are working in electronic waste. Of course, I will give number 10 to the Umicore's. That's my previous employer as well. I enjoy working with them. They are very professional people. They are doing a marvelous job in the refining of many the metals. I would recommend, if somebody is interested, to look at their website, look at the literature. Autotech, we work in Australia with Autotech as well. They are also working in this area. Ronsker Smelters, I think it's in Sweden or Norway, and Norenda in Norway. Ronsker Smelter Test, Umicore Trials again, Dova Mining in Japan. Japan, the Olympics that was going to happen. The medals they made from electronic waste recycling. That was a very good, they extract the gold and silver from electronic waste to make those medals. Some work by Days Patent, some other works in Russia as well, and Rubis Recycling in Germany as well. So all of them are working in this field to extract the metals. This is a Umicore integrated smelter facility. They have the lead smelting and they have the copper smelting. I don't want to go in details, but they have the lead smelting as well. They extract the lead, and they also have the copper smelting, integrated plant. So in this case, simultaneously, they extract the metals, precious metals out of that. Here you can see we have the base metals, copper, base metal lead, base metal nickel. And you can see what kind of metals you can attach with those base metals to extract at the end. Okay? For example, in copper, gold, platinum, cesium, iridium, rhodium, and platinum, and also silver you can get with the help of copper. Nickel, you can similarly find the metals in there. So Umicore has a very good control of the of emissions of gases. They have ISA smelter, the smelter. Then they have the filter dust and the dust bag houses, and also all of the sulfuric acid. The sulfur oxide goes to the sulfuric acid plant, and the off gases, like we have sulfur oxide, some noxons, some other gases, dioxins. So they detect like regularly to avoid any kind of environmental damage. So very good work, very professional work, and a very efficient and profitable business at the moment. Similarly, we have the Ronsker smelters as well. They're also working in this area. They're using the electronic scrap. Similarly, the rest of the process are all same. I don't want to go in details. Similarly, we have the Norenta process, is a copper smelter. We have reactors, and put the electronic waste in as a part of the feed material. And at the end, you can extract gold and silver similar you get from a normal copper smelting route. Okay, what's the way forward? We can first we can reuse the material, and we can recycle, and we can manufacture things from there. Try to close the loop of the material. And if we go in further details, small scale recycling approach could be useful, as we given in our work. If you have a big cities, you have a good collection centers there. You collect the electronic waste there, and then you can have a small scale recycling facility. If cities are apart, like the case is Australia, okay. But if you have a congested cities, so you can transport the electronic waste easily into a one unit, and you can process over there. I mean, there is lead-free solders are developed. It's not something new, but again, we try to make the lead-free solders like more efficient with good conductivity, so that we don't need to use gold and silver much in there. Okay, so and also circular economy approach. Overall approach should be that we have to have a zero waste. The material we use, we process, recycle that, and bring into the loop again. And also responsibility at individual and global scale. Thank you. Questions?
Okay, thank you, Dr. Abdul. We have 2 minutes for questions.
I'm
Okay,
sorry, actually, as I said, I have now 2 hours lecture at after
right.
2 minutes. It's
Yeah,
okay.
so Dr. Abdul have other lecture like after this, but he's happy to ask questions. So to answer, I mean. So yeah, ada pertanyaan? Do you have questions, students?
Hello.
Yeah. Okay, Fadlan.
Thank you, Mrs. Winnie, for the time. My question is, we know that scraps contain so many form of metals. My question is there a minimum percentage of metal that contain in the scraps to make it economically feasible to be recovered? Or is there a rule of thumb of how much kind of metals that can be recovered from a single electronic waste recovery facility? Thank you.
Okay. Yeah. I think it's a good question. What you can do, I recommend to look at our papers. Okay. So these 2 papers are there, so you will get a good information from there. But again, it's depending on the economic point of view. If you take the printed circuit boards straight away, from the electronic waste, that contains about 20% copper. Okay? And that also contains some plastics and some others. So bringing that printed circuit board straight into the hydrometallurgical route, for example, is not recommended. Okay, you need to process it, shred it, and extract to enrich in terms of the metal component, to increase the metal component, to remove the plastic. Okay, but in the pyrometallurgical route, you can bring as such the printed circuit board, because the plastic that are hydrocarbons, these hydrocarbons, when they will go into the pyrometallurgical route, they will burn and they will provide extra heat. They will replace coke. So my question is, overall, is this one, that is depending on the situation. There is no 1+1. There's no right or wrong answer at the moment. But of course, you need to carefully look for your process itself to decide. Which route you're gonna adopt.
Okay, one more question. Okay, Fadlan, that's a good question.
Hello.
Yeah, hello. Yeah.
Okay.
Okay, Ardi.
Thank you, Miss Pini, for the time. I want to ask question. Which process is more effective, production-wise and energy-wise? The production of copper from primary source such as chalcopyrite, or the copper production from the scrap metal? Thank you.
Yeah, which are the more efficient, from primary sources or secondary sources?
Okay, it's look, the bigger industries, for example, the Noranda process, the Ronsker smelt, they are the primary copper smelters. What they use as a primary input material, as they replace the input material with the printed circuit board. But Umicore, they are not primary copper smelters; they are secondary. They use in the secondary as well. So basically, it's all depends. How pure you have printed circuit boards are. I know many companies nowadays, they do not process the electronic waste 100%. What they do, they collect it, they shred it, and they extract the copper and the lead and the gold and silver in there. Then they can go into put into the secondary smelter. They should not go into primary smelter. In that case, I should recommend the secondary smelting is the most efficient.
Right. Okay. Thank you. Looks like it is more than 2 o'clock, so 1 hour has finished. So I would like to give appreciation to Dr. Abdul. So I would like to share screen and then send it to you. Oh, sorry, virtually. Yeah. So this is
Thank you.
a certificate of appreciation from our chair, Dr. Arsa Putrawan, for your contribution to our guest to lecture, the TK 4047 Fundamentals of Process Metallurgy. All right. Lastly, before we finish, if you want, you can open your videos and we can have a take a picture together. It's gonna be good. Okay, and then thank you for listening. I know it's been a long day for you, ya. Sudah lama dari pagi. You're listening to Zoom for the seminars, right? Okay, but I hope this will give you more information, more insights about recycling, and also it can be a topic for your paper as well. So at the end of the semester, the students need to make a group report, group report that one. Okay, I'm gonna take a picture. Okay, udah siap semua? Okay, 1, 2, 1, 2, 3. Okay, the second
Thank
page.
you. Thank you, everyone.
Yeah, okay.
And I would love to come again. And thank you, Winnie, for your invitation.
Right.
I wish you all the best for your students, very smart students, and for you as well. Thank you.
Okay, thank you, Dr. Abdul. Yeah, you can leave now. Okay. Ya. Oke. Baik, para mahasiswa, terima kasih atas kehadirannya. Hari ini cuma 1 jam saja. Jadi silakan jangan lupa isi absen dan kita ketemu besok untuk bicarakan tentang elektrometalurgi, tentang electrowinning yang tadi diceritakan oleh Dr. Abdul ya. Oke, sampai ketemu besok. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Terima kasih banyak.
Okay.
Terima kasih, Bu.
Kita tutup ya. Terima kasih.